How do machines truly compare two complex datasets without knowing their underlying density? The answer lies in maximum mean discrepancy, a powerful metric that compares distributions by simply comparing their means. Imagine you have two sets of data vectors generated from unknown probability distributions. Instead of estimating complex density functions, which is often impossible, MMD offers a direct way to select variables that discriminate between these two distinct sources. MMD is defined as the distance between feature means in a reproducing kernel, Hilbert space. By mapping data points using a kernel function, we transform the problem into comparing the mean embeddings of the distributions within this high-dimensional space. We can also view MMD as an integral probability metric. A recent breakthrough involves integrating this discrepancy over all one-dimensional projections of the data using a Gaussian kernel to derive a closed-form expression for similarity. In practice, this is implemented efficiently in frameworks like PyTorch. The process calculates similarity matrices between the source data and target data, finally computing the distance to determine if they come from the same distribution. This tool is invaluable for machine learning tasks like domain adaptation and generative model evaluation. It allows us to measure how closely a generated sample matches the real world without needing to calculate difficult density probabilities. Ultimately, MMD proves that comparing distributions can be as simple as comparing their transform means. This elegant mathematical approach bridges the gap between abstract probability theory and practical computational statistics. MMD revolutionizes how we assess distribution similarity in AI. Have you used kernel methods in your own projects? Share your experiences with this metric in the comments below to help others understand its power.